All right, so chapter 4 is all about electrons. This entire chapter is just discussing electrons. Okay, so the study of light led to the development of this, what we now know as the quantum mechanical model of the atom. We're going to talk about the simpler models before the quantum mechanical model was discovered. This is the most recent. It is very, very complicated, but this is what kind of led to more discoveries about the electron. So a photon is just a particle of light that has energy. Right? And so this, I'm going to use this ER as an abbreviation, and don't get it confused with biology, right? In biology, ER is like endoplasmic reticulum or something. And in this class, it's electromagnetic radiation, and all this means is some sort of form of energy that can move like a wave. Now, there's plenty of electromagnetic radiation that you guys have heard of. You've heard of X-rays, you've heard of UV rays. Obviously, visible light is the light we can see. I'm sure you've heard of infrared. That's what IR stands for. And microwaves and radio waves and then gamma rays. And so I listed these in order of the most energy to the least energy. Okay? And all electromagnetic radiation will move at what's called the speed of light. And the speed of light is going to be represented by the letter C. So that's our new letter. And no, you don't have to memorize it, but you will have to know how to use it. C, oopsies. It's way too big. C is a number, and it is, and this is only true in a vacuum. So like your room is not a vacuum, so these things won't move at the speed of light in your room. So let's see. C is going to be, I have it down here. Jeez, I have it down here. 3.00 times 10 to the 8th meters per second. I just want to show you that there's another way to write this. It's this, ms minus 1. Minus 1 means this is in a denominator. So like if you have x minus 1, it means 1 over x. So s minus 1 means 1 over s. So it's meters over s. I just want to show you a different type of notation that you might see. I will tend to write it this way most of the times, but this is not wrong. I just want you to be aware of it. Okay? It looks like I had a couple chats. Sorry, guys. Okay, so let's keep going. Again, you guys have access to my notes throughout at any time, so you can, if you can't finish copying them down, you can copy them down on your, on your own time if you want, if you're choosing to copy every single thing in my notes down. So C stands for the speed of light. This is how fast light moves in a vacuum, and this is any kind of light. Now, this is what is kind of interesting. I know that you're not used to this. These are gamma rays are a form of light. It's not the light we see. The light we see is called visible light. X-rays are a form of light. UV rays are a form of light. Infrared rays are a form of light. They're just light that we can't see. The only light we can see is what we call visible light. So this is how fast they move in a vacuum, which is the speed of light. All of these things will move that fast in a vacuum, which is really, really fast. Okay, so I gotta move this over. Maybe I'll put it down here. Okay, so in the grand scheme of things, so these are like radio waves down here. They're pretty big waves, and then like gamma rays are really, really short waves. In the grand scheme of all of the light that exists around us, all of these things are light. We're technically like fairly blind. Like this is the only region we can actually see. You can't see radio waves, you can't see microwaves, you can't see infrared, you can't see UV, you can't see X-rays, and so forth. So like this light, this like tiny little piece of light that there is of all of these is the only part that we can actually see. So we're technically almost, blind to most light that does exist in terms of what we can actually visualize. Okay? So again, this is another copy, a copy of an electromagnetic radiation spectrum. So you've got your really low energy waves down here and your really high energy.
Draw that.
What's that?
We draw it.
No, because you have a copy of it. So these are your high energy, super high energy, super low energy, and then the light we see is somewhere in the middle. If you want to look at it this way, like up until visible light, you're good in terms of how harmful it is. After visible light, you know that UV light is harmful, right? It can cause, like UV light from the sun can cause skin cancer. You know, X-rays can be harmful, right? That's why you wear like a little lead vest when you go to the dentist and you put it over you to prevent the X-rays from penetrating your skin and hitting your organs. And then gamma rays are the worst, the absolute worst. Gamma rays would hurt you. They use isotopes that release gamma radiation in chemical warfare, or they used to. They haven't in a while. These can penetrate through your skin and get into your organs and damage or pretty much really harm you or kill you. Okay, so like these guys are low energy, they don't bother you. After visible light is when you start to get the higher energy, way more harmful types of light or radiation. Okay, I'm going to use the word light and radiation kind of interchangeably. All right, so if you did not know the order of the colors, you do need to know, sorry, it's kind of hard to see this one. You do need to know them now. So Roy G. Biv is a acronym to remember all the colors of the rainbow. So red, orange, yellow, green, blue. I stands for indigo. Sorry, it's kind of hard to see with that background. Indigo, and then V is violet. Please don't call it purple. I know it looks purple, but we call it violet. These are the technical colors of the rainbow. And this is all we can see of that whole electromagnetic radiation spectrum. This is it. This is all we can actually see with our eyes. It doesn't mean the other stuff doesn't exist. We just can't see it. Okay, so Roy G. Biv is a way to remember all of the different colors of the visible spectrum. Okay, so white light, so like general white lights are made up of all of the colors of the spectrum. If you were to shine white light at a prism, the prism has the ability of breaking the white light apart, and that's why you see the rainbow, because the white light is really split up into all colors of the spectrum. So you can see all the colors, red, orange, yellow, green, blue. They didn't include indigo on here. And then violet. Indigo is just like a darker blue right before purple, or violet, excuse me. See, I just did it. Okay. So we're going to do math in this chapter. So because we're talking about electromagnetic radiation travels in waves. So this is the Greek symbol right here, lambda. When you actually write it, I write it like this. It looks like a TP or like an upside down Y, lambda, and it stands for wavelength. Okay, so you will need to know that, wavelength. And wavelength is just the distance between two waves. Wavelength. This is the top of one wave. This is the top of another wave. You could also do the distance between the bottoms. It wouldn't matter. Just it's the distance between two waves. Wavelength. V is, I think it's the symbol nu. I don't really remember. But V is going to stand for frequency, and that's how often you're seeing the wave. So like if you have a wave that's like really long and far apart, you're not seeing it as frequently, as opposed to waves that are really close together, you're seeing them more frequently. They have a higher frequency. So frequency is how often. And the unit for it is 1/seconds, or S minus 1. Wavelength is measured in meters or nanometers, some sort of distance kind of unit. And then S minus 1, or 1/S, is frequency, how often per second you're seeing the wave. They sometimes call frequency Hz, which is a hertz. it means the same thing as 1 over s, or s minus 1. A hertz is a unit for frequency also. And then they are inversely related. So this is the speed of light, c. It's a number, right? We just went over that number earlier. 3.00 times 10 to the 8th meters per second. And what inversely proportional means is when the wavelength gets bigger, the frequency gets smaller. They do the opposite of each other. When one goes up, the other one goes down. So this should make sense because, I'm going to erase this again. If you have a wave up here, like this, and then below it, I'll do this wave. This is a big wavelength relative to the one below it. This is a higher wavelength rather than this one. This is a lower wavelength, right? This is a shorter distance, smaller distance. And you don't see the waves as frequently. Like, I only see 3 waves in the same amount of time. So the frequency, V, went down. Now, with a shorter wavelength, I see the waves a lot more times. 1, 2, 3, 4, 5, 6, 7, 8 waves in the same amount of time. So my frequency went up. I saw the waves more frequently. So that's what an inverse relationship means. When one thing gets bigger, the other thing gets smaller. Okay? So you need to know the different parts of the wave. So for this part specifically, I would draw it. So just draw like 2 waves. The distance between the 2 waves is called the wavelength. The top or peak of each wave is called a crest. The line I kind of drew through them to cut them in half is called the origin. And we're assuming the waves are symmetrical, okay? So the difference between the origin to the top is known as amplitude. It's like how tall the wave is. And then this bottom under here part of the wave is called the trough. It's kind of like, you know, horses eat out a trough, and a trough is like a bin that they put their heads into and kind of get in. So like this right, oops, sorry. So it's like the horse trying to get in here to eat the trough, right? So the trough is just the bottom, the under wave, okay? So the top of the wave is called the crest, and the bottom of the wave is called the trough. I'll give you a second to draw this if you need to. All right. Again, you will have these notes on Canvas that you can access at any time you need to. So let's look at wavelength. That's what this symbol stands for, and frequency. Okay, we're going to compare these 2 waves. So look, this is a shorter wavelength with a higher frequency. You see the wave more often. This is a longer wavelength with a lower frequency. So big wavelength, not as frequent. So if I'm having you identify which is gamma, which would be a gamma radiation and which would be a radio wave, you would want to use your electromagnetic spectrum. So let me pull it up. So here it is. So look, gamma radiation is down here. And if you look at wavelength up here is labeled in meters. If you look at the powers of 10, 10 to the negative 11 is a really, really small wavelength, okay? Radio waves are in this region, 10 to the 1, 10 to the 3. So these are bigger wavelengths. So bigger wavelength, smaller wavelength. Remember that the negative powers mean a small number. So if you were to pick which one would be gamma and which one would be radio relative to each other, this one should be gamma. It has a shorter wavelength, and this one relative would be radio waves, which are longer wavelengths. Yes, you will get the electromagnetic radiation spectrum on the test or the quiz. You will get to use it. So you don't have to like memorize the order necessarily. Okay? So now if I ask instead, which one would be visible light or which one would be IR stands for infrared, let's go back to our electromagnetic radiation. Oops, not that. Our electromagnetic radiation spectrum right here. I'm going to just delete this. Okay. So it's infrared, which is right here, and visible light, which is right next to it. Well, infrared is 10 to the 5th. This guy is 10 to the negative 7th. So in this chart, wavelength is decreasing as you move to the left in this chart. There is no reason they can't make a chart that is flipped, but the numbers wouldn't flip. The numbers would stay the same. They could just write it backwards, where radio waves are over here and gamma is over here. So look at, if this is 5 and this is negative 7, visible light is obviously smaller in wavelength. That's what we're looking at, is smaller wavelength than infrared. So a smaller wavelength would correspond to this guy. So visible light is a shorter wavelength based on my chart, and then this guy would be infrared, which is a longer wavelength. Do you have any questions on how to identify the waves using the chart? Okay. So again, here's our chart. This is just another chart. Our visible light is made up of Roy G. Biv right here. And we'll talk about nanometers in a minute. Visible light falls in. Oh, I wasn't allowed to draw on this. Visible light falls into the 10 to the minus 7 region. Okay. So we're going to start to do math. We're going to do 2 sets of math today, and then I'm going to set you free to work on your homework for the weekend. You're going to have 2 assignments. One is going to be a reading assignment, and the other is going to be a worksheet doing math. So this says a certain violet light. Okay, so the light is violet. And I give you its wavelength, and now this is going to be new to you. NM stands for nanometers. It's a metric unit. Nano is a prefix just like centi and kilo and deci, but it means something. Does anybody know what nano means? What number? You will have to know after today. 1 nanometer. Okay, are nanometers small or big? How about that?
Small.
Good, very good. They're small. They're very little. So you need oops, I'm doing this backwards. You need a lot of them to make up a meter. So for the word nano, think 9. 10 to the 9th nanometers in 1 meter. Nano 9. Nano 9. Now you can write this opposite. You could do sorry. 1 nanometer is 10 to the negative 9 meters. I do not prefer this way. I would really, really prefer if you use this way, just so we don't have to deal with negative exponents. This isn't wrong right here. It's just, instead of dealing with negative exponents, let's just do it this way. Again, I'm not going to penalize you if you do it this way. The 1 nanometer is 10 to the negative 9th meters, but I would prefer this way. So in order to do these problems, so I give you wavelength, I ask for frequency. So in order to do these problems, we have to have an equation. So what equation do we use? Well, you have to go back to your equation from the beginning of this chapter and see that this equation has wavelength and frequency in it. And because
what's the equation for nanometers? I can see the last
10
part.
to the 9th nanometers is 1 meter. So you go, okay, this equation has wavelength and it has frequency, and you go, oh, but I don't have the c. Yes, you do. C is the speed of light, and it's a number, and it's 3.00 times 10 to the 8th meters per second. So you do have c. It's right here. Okay, it's like you can kind of consider it a constant. So you're going to rearrange this, right? They ask you in this problem to solve for frequency. So you go to your equation and you find which one, you find which symbol is frequency. So you're going to have to get comfortable with this. This is your symbol for frequency. So I'm going to rearrange, and I'm going to divide both sides by wavelength, and that will give me this. This is just basic algebra. You divide both sides by wavelength. The wavelength is gone, and you're left with frequency. So C is 3.00 times 10 to the 8th meters per second. That's C. Divided by, now, you cannot plug in nanometers. Let's see, what was the nanometers I gave you? 413 or something? Yeah, 413 nanometers, which corresponds to violet light. Anybody know why you can't plug nanometers into this equation? What's this? Meters. So the units have to match or they won't cancel out properly. So in order to do this problem, you have to turn the nanometers into meters. Now this is, a lot of times there's calculator issues, so please have your calculators handy. So 413, we're going to do a metric conversion, nanometers, dimensional analysis. Please write your dimensional analysis just like me. I was noticing on your quizzes that your guys' work was all over the place, which we'll talk about Monday. I need it to look just like this. I think that a lot of you are struggling is because you're trying to do it your own way. So the thing we don't want anymore goes on the bottom, nanometer. The thing we do want goes on the top. And the conversion factor is for every 1 meter, it is 10 to the 9th nanometers. So on your calculator, let me grab mine. On your calculator, you hit 413. Let me see if I can see you guys. So 413 divided by. Now, you're going to do either, some of you have a 10 to the x button, but you're not going to use your EE button for this one. You're going to do 10, and then you're going to hit the caret button. It looks like that. It's like a upward half triangle. That means 10 to the, and then you hit 9. And you get 4
Can you draw what it looks like? Because I can't see your screen that well.
It looks like this on most calculators. Some of you have a 10 to the X button though, so I'll have to, everybody's button is different, depending on what kind of calculator you have. What kind of calculator do you have, Nathan?
Texas Instrument.
Okay, can you just, if you show me a picture of it, I can find the button for you.
Email or maybe
just share your screen with me.
Yeah.
Okay, hold on. I gotta find you. So for this answer, I'm going to write it in scientific notation. In your calculator, it should be 4.13 times 10 to the negative 7th meters. Remember, nanometers cancel. Now, If you did not get this power of 10 right, it is because you're using your calculator incorrectly. When class is over, which I'm going to finish fairly early, hopefully today, when class is over, I can help you with your own personal calculator once everybody kind of checks out, just to make sure we're using the correct buttons. So this should be what your wavelength is. So having said that, that goes in the bottom. It's speed of light divided by wavelength. So 4.13 times 10 to the negative 7th meters goes in the bottom. Meters cancel, and you're left with, be careful, this is 1/seconds, which is what a unit of frequency is. So in your calculator now, you take 3.00 and then you hit your EE button times 10 to the, let me see. And then I hit 8. And then I hit divide. And then I hit 4.13, and then you use that EE button again, or EXP button. Oops, I put a comma in there on accident. And then you hit -7. And your answer should come out to be 7.26 times 10 to the 14th. And yes, you have to put units. 1/seconds. This seconds is in the bottom. It's meters per second. Or you could technically write it as or S minus 1. That means the same thing. Or all of these things mean a hertz. I don't care which unit you use as long as you put a correct unit. It is not seconds. It is 1/seconds. So that is the frequency. Do you have any questions before we keep practicing? We're going to do a bunch more, 2 more practice problems like this. And then we'll move on. Okay, so I'm going to go to number 2. A certain blue light has a frequency. Oh, actually, I want to go back real quick to here. A certain violet light, and I give you a wavelength of 413 nanometers. Well, let's look on our electromagnetic radiation spectrum. Look at down here. This is in nanometers right here. This is nanometers down here. Okay, 413 is like right here. Oh, look, that is violet light. Like it matches up. Okay. And then again, these are going to be 10 to the -7 powers for the visible spectrum in meters. Okay, so a certain blue light, and I give you a frequency, so that's V, and I want wavelength, that's lambda, or this upside down Y TP looking thing. So how do I do it? Well, I have an equation that has wavelength and frequency in it. So 6.26 times 10 to the 14th hertz. So C equals wavelength times frequency. I'm solving for this one now, wavelength. So I divide both sides by frequency. So C, speed of light, over frequency is wavelength. Well, what is the speed of light? It's a number, 3.00 times 10 to the 8th meters per second. Okay, this is a constant. What's frequency? Well, they gave it to you in the problem. It was 6.26 times 10 to the 14th. Now, they called it a hertz. For unit's sake, I'm going to call it 1/seconds, okay? Because it'll be easier to see how the units work out this way. It means the same thing. I'm pretty sure that was the frequency. I'm double checking. Okay, so let's plug and chug. Plug the numbers in. So let's see, speed of light. 3.00 times 10 to the 8th meters per second. That's C. Divided by frequency, which was 6.626 times 10 to the 14th hertz, which is the same thing as 1/seconds. So look at, my seconds cancel and I'm left with meters. Meters is a unit for wavelength. So you take in your calculator and you hit 3, EE button, EXP button, 10 to the X button, whatever button it is for you, and then 8, and then you put divided by 6.26, and then you hit that EE button again, or EXP button, and you should get 4.79 times 10 to the negative 7th, and then what are the units? Meters. Now, I didn't ask you for it in nanometers, but I want you to convert it to nanometers. So let's practice that. I'm doing that on purpose. You need to get good at converting to nanometers. So if I said, okay, well now I want this number in nanometers, you would set up your dimensional analysis. Meters would go on the bottom. Nanometers would go on the top. There's 1 meter in 10 to the 9th nanometers. So how would you do this in your calculator? You would do 4.79 times 10 to the negative 7, and then you would hit times, and then you don't use your EE button this time. You do 10 exponent 9. And everyone, I'm going to give you a second to try that. Make sure you're using your calculators correctly. Anybody have an answer? Oops, 479 nanometers. If you did not get this, it is likely a calculator issue. So let's see, did anybody else get 479? Yes, good, awesome. So 479 nanometers, let's look at our electromagnetic radiation spectrum. This problem said it was blue light, right? So if this is 400 and this is 500, 479 is like right around here. Oh, look, it's blue light. Okay, it does match, it makes sense. All right, I'm gonna skip, or we'll do, what time is it? 9:17. I'm just gonna do the second part of this. If a light has a wavelength of 636 nanometers, what color is it? So let's go to the electromagnetic radiation chart. 636 nanometers. So here's 600 nanometers. Here's 700 nanometers. So 650 is like halfway here, right? So 636 is somewhere around here. It's probably an orangish yellow, or yellow or orange probably would be an acceptable answer. It's like somewhere in between that. That's what color it is based on my electromagnetic radiation spectrum. I'm just going to do that part. We're going to do 4 and then I'm going to move on. So an electromagnetic radiation spectrum is measured to have a frequency, and I give you frequency in hertz, and I say what is its wavelength, okay? And then at the end I ask what type of radiation it is. So let's do the calculation first. So C equals wavelength times frequency. They ask for a wavelength, so I'm going to rearrange. C divided by V is wavelength. Well, C is a set number. It's 3.00 times 10 to the 8th meters per second. There's my C. Divided by frequency goes on the bottom. Oop, I don't remember what number they said it was. 5.54 times 10 to the 9th. So 5.54 times 10 to the 9th. Now they called it a hertz, but for the sake of units, I'm going to call it 1 over seconds so that we can see how the units cancel, right? The seconds here and the seconds here will cancel, and we're left with meters. So in your calculator, 3 EE button, 8, divided by 5.54 EE button, 9. And it comes out to be 0.0542 meters. I'm going to just write this in scientific notation. I'll show you why in a second. That's 5.42 times 10 to the negative 2 meters. Okay, I just rewrote this in scientific notation. The reason that I did this is when you go to look up radiation on the electromagnetic spectrum, you'll notice, because it asks what type of radiation it is, or light, radiation or light. So if you look on your spectrum, they go by powers of 10. Everything is like by powers of 10. It's not exact numbers. So writing in scientific notation helps you.
Miss Murphy, my answer got 54 point, wait, no, 5.45.
So you probably either put something in wrong, or let me make sure I put my numbers in correctly.
No.
Did I write a number down? You don't have to write in scientific notation. You just have to always write to the right number of sig figs. I think that maybe you wrote the number down wrong, Nathan. Try looking again.
Yes. 3.0008 divided by 5.5 with 9.
No, 5.54.
That looks like a Y.
Okay, well, it's a 4. Okay, so the power of 10 is helpful. It's not necessary as long as you write with the correct number of sig figs, but the power of 10 is helpful when you look at the electromagnetic radiation spectrum, because you should notice all of the numbers are given as powers of 10. So that's why I rewrote it. Look at powers of 10 down here, powers of 10 down here. So this is what? 10 to the negative 2. So this is all you have to focus on to identify the radiation, is just the power of 10. So you go to your chart and you go, okay, where is 10 to the negative 2? Well, here's 10 to the negative 1. Here's 10 to the negative 3. So 10 to the negative 2 would be somewhere in between here, which is microwaves. Questions? So again, you would have the chart for something like that. Okay, so these are our light problems for light moving like a wave, okay, traveling through space. The problem is that light also can behave like a particle, and we can also measure not only the frequency and wavelength, but the energy of light. Remember, photon is just a particle of light or particle of radiation. So this is another equation that we'll have. It's E, which stands for energy, and then it's H, which is a set number, meaning you don't have to memorize it. It is always this number. This is called Planck's constant. 6.626 times 10 to the negative 34th joules times seconds. And then the frequency again is hertz, 1 over seconds, s to the minus 1, whatever. This is the same normal frequency. So this is the equation for determining how much energy or frequency something has based on this equation. Now, what do both equations have in common? Both equations have one of the same variable. Who is it? It is frequency. Meaning, if you know frequency from one equation, you can, or if you're trying to find frequency, you can solve for it in one equation and then plug it into the other equation, or vice versa. You could solve for frequency using energy and plug it in up here to then get wavelength. Okay, so these equations can be used together, is what I'm telling you. So let's do practice. Energy is in joules, which is represented by the letter J. Sometimes they do them in kilojoules, which is just another unit for energy. They mean that's just a prefix, a metric prefix in front of it. So we're going to do these energy problems, and then we'll stop for the day, and I'll let you start on your homework for the night and the weekend. Okay, so the next question. It says, a type of electromagnetic radiation has, let's skip 5. Skip 5. Infrared radiation has a frequency of 5.87 times 10 to the 13th hertz. Okay, so there's frequency, which means I have V right here. How many joules of energy? So I want to know E. Does each photon just means particle, the particle contain? How much energy does it have? If it has this much frequency, what is its energy? Well, we have an equation for that. It is E equals hv. This is a constant, just like in the other equation, we had C as a constant. You don't have to memorize it. I will give it to you. This is Planck's constant. So they ask for energy. You have H, because it's a constant. They gave you frequency in the problem. You just plug them in and multiply. It's not any more complicated than that. So H is 6.626 times 10 to the negative 34th joules times seconds. And then frequency, I got to go back to the problem. I don't remember what it was. Frequency was 5.87 times 10 to the 13th hertz. Oops. So again, for the sake of units, I'm going to rewrite hertz. Oh gosh, I already forgot. 5.87. Okay. 0.87 times 10 to the 13th. Now, I'm not going to write hertz. I'm going to write it as 1 over seconds, and the reason being is because then I'll be able to see how my seconds cancel out, and I'm left with joules, which is a unit for energy. So you just multiply these two numbers. 6.626, you hit your EE button, negative 34, times 5.87, you hit your EE button, 13. I'm going to wait for some answers and see what you get. This is 3 sig figs, so your answer will be 3 sig figs. It's 3.83. Now, don't forget to read your whole calculator. Times 10 to the, what is my power? Oh, wait, 6.626. Hold on. I think my number might be slightly off. I hit the wrong. Oh, no, it's right. 3.83 times 10 to the, what's my power? What'd you guys get for a power? Anybody?
Negative 20.
Yes, wonderful. Negative 20. And then the unit is joules. So,
Miss Murphy?
yep.
Yeah, I got a different.
Okay, so we're going to try another one. All right, so number 7. What is the frequency? Hey, Nathan, will you mute yourself? What is the frequency? So that's what letter? That's V of a photon. This just means particle of light. And I give you its energy. So I give you E. Okay, so the equation that has energy and frequency is E equals hv, where we always know h. It's Planck's constant, 6.626 times 10 to the negative 34th joules times seconds. Okay? And this time I gave you E also, and you're trying to find frequency. So let's go back. I don't remember what the numbers were. So it's 1.56 times 10 to the negative 16th joules of energy. So if I rearrange to solve for this, it's E divided by H is frequency, right? We divide both sides by H to get the frequency by itself. So E, oh, look, I already forgot what it is 1.56 times 10 to the negative 16. 1.56 times 10 to the negative 16th joules divided by, this is Planck's constant right here, so this number just goes down here. So 6.626 times 10 to the negative 34th joules times seconds. So look at my joules cancel, one on the top, one on the bottom, and now look, this is seconds in the bottom, so that is the same as 1 over seconds, or S minus 1, or hertz. They all mean the same thing, which is great because we are solving for frequency, and these are the units that belong to frequency. So I'm going to give you a second to calculate it out. Hopefully I don't make the same mistake I made on the last one. So let's see, I get 2.35 times 10 to the, what power did you guys get?
17.
17, me too. Okay, and that's the frequency. So it says, what type of radiation is it? Oh, well, let's look on our chart. I have frequency, so we're going to use the frequency part. What did we say? It was 10 to the 17th? Now, frequency is at the bottom part of the chart, okay? Frequency is down here, so I want to look for a 10 to the 17th. It looks like, so this is 16, this is 18, so 17 is like right here. So these would be X-rays, okay? Now, it says, what is the wavelength of the radiation? Well, now that we have frequency, now that we have frequency, we can solve for wavelength because we have an equation that has frequency and wavelength in it. What is it? C equals wavelength times frequency. So we use the E equation to get frequency, and now we can use the frequency to plug into here to solve for wavelength. So I'm going to erase this. I'm going to rearrange to solve for wavelength. So C over V is wavelength. I'll do it up here. So C is speed of light. It's a number. You have it written down. Meters per second. Divided by frequency. Well, where did frequency come from? Well, that came from the first part of the problem. 2.35 times 10 to the 17th 1 over seconds. So seconds cancel and we're left with meters. So let's calculate it out.
No, dude. Get down.
So I got 1.28 times 10 to the negative 9th meters. Now, again, we could have used this to look on the electromagnetic radiation spectrum. We just would look at the top part because the top part is where the wavelength is. So wavelength is up here. So it's X-rays. It doesn't matter whether you use the wavelength or the frequency because both are options on here to look at, powers of 10. So this is X-ray radiation or X-ray light if you want to call it that. How are we doing? So I'm going to stop here. So these were all the answers. So you have all the answers on here too for all the problems. Okay. So this is just, remember, we have two equations. We have both equations have frequency in common. They both have frequency. So if you know one of the equations, you could solve for frequency and plug into the other. So like you could use the top equation to solve for frequency and then plug the frequency into the energy equation. And then remember, C and H are constants. You don't have to memorize them, but you just have to know how to use them and their units. You always have to label sig, do, sig, figs, and units for any math we do in here. Okay, so I'm going to set up your assignments right now on Canvas. You guys can head out if you want. I'll stay here if you have questions. But I'm going to post the assignments for tonight and tomorrow and stuff that's due by Monday. Now on Monday, you need to come ready with your work from your quiz because we're going to go over it and you're going to do corrections. Okay, so right when class starts, I want you to have your calculator ready, your periodic table ready, and your work for your quiz that you sent me. I want it ready because you're going to do corrections and then you're going to turn them in. Those should be free and easy points. So I'm going to mute myself real quick. You guys can hang out or you can head out, but I'll be posting the assignments on Canvas like right now. It's going to take me a minute, but I'll get them up. I'll also be posting the notes as well and this lecture.